Hey guys, welcome back. This is part 3 of the DQN coding implementation, deep Q learning. Now, if this is the first video you've clicked on, I have two earlier parts of the series where we go through all the different steps in needing to code this project, and this is actually the final part. Now, I know in the previous videos I said there would be 4 parts, but actually I was able to condense it down to 3. So this will be the final part where we get to wrap everything up and see our agent play the video game. So let's get right back into it where we left off. Okay, so now we're back at the training loop, and as you can see, we now understand what this line of code means. It takes the state, passes it through the neural network, and it brings back which action we should take, 0 or 1. So in either case, we have the variable action which represents which action we should take. If it was a random action, that means this number is a random number. But if it was through exploitation, this number is a very specific number which represents the best action that we should take, hopefully. So next thing to do is to take the action, right? So this is actually going to be the exact same process up here. In fact, I can even copy and paste it, although it might mess up with the indentation, which I believe, yeah, so I'll just have through all this. But if you remember, we can take action, which is either exploration or exploitation, and we can pass it through the environment. So our agent takes that action, and we want to take this next state that we get, the reward, and whether or not the episode finished. Now we can create the tuple of an experience which represents the original state. Remember, we had this state when we reset the environment, the action we took, the reward we got, done, the next state, the state afterwards. And then after that, we append this experience to the replay memory, which we initialized up here. And finally, we make state we set state equal to S1. So now the initial state has become what the quote unquote next state was. So we can prepare ourselves for the next round of things. Okay, so there's that. Now we're going to get into the actual training the neural network phases, where we take the experiences and we pass them through the neural networks in order to train it to come up with better and better guesses of the Q values. Okay, so the first thing we need to do is get a batch of experiences to train our neural network with. Remember how we were talking about the batch dimension? Well, here's in the case where we actually use it, because when we're training it, we actually are going to send multiple states at a time. So we need the batch dimension. So first thing we're going to do is take a random batch of experiences from the replay memory. So we are going to say experiences equals random.sample replay memory. And remember, we want to make the size the batch size. This was the variable we initialized earlier. And now that we've done this, we are going to do something a little bit clever, because you see right now the experiences is a list of one experience after another stacked up against each other, which means, state, reward, state 1, action, and it has each experience is its own little group, and then it has another experience. But we want to split it up differently. We want to have one list, which is all of the states in a row, another list, which is all the actions in a row, another list, which is all the rewards in a row, and the same thing for whether or not it's done and for the next state. So we need to take this batch of experiences and we need to split it up. So each part of the experience is its own batch. So let me show you how we're going to do that. So first thing we're going to do, I'll show you how we do it for the states. So we'll say states equals E0 for E in experiences. So what does this do? Basically, this creates a list where it goes through each experience and it only takes out the thing in the 0th place, which is the state. If you remember, in the experience, the state is the first thing. So it takes the state for each experience and it appends that state to a new list, which is the states list. So this will take each single state from the batch and make it into its own little batch right here. But we want this as a numpy array. So we're going to do np.array over, np.asArray over this. And it's very helpful to make this into a numpy array a lot more efficient. So now what we're going to do is I'm going to copy this and paste it 5 times. But here's the thing, because we need to do it not just for the states, for the actions, and for the rewards, and for the dones. Not correct grammar, but that's how we're going to call it. And then we're going to call this, let's see here, we'll call it new states. Except for states, it was the 0th one in the experience, the first one, but I'm saying 0th so because it was represented by the number 0. Actions was number 1. Action was the next one. Reward number 2. Reward was the next one. It goes 0, 1, 2. Then dones is 3, and finally new state is 4. So now for after this, we've taken the overall batch of experiences and split it up into a batch of states, a batch of actions, a batch of rewards, a batch of dones. So if you want to see what this looks like, actually, why don't I put this into a new... First, we can show you just what experiences look like. Print experiences. As you can see, it has the action, the state, the action, the reward, the done. It's a whole mess. But if we take the states, all of a sudden, now we have just a list of each state. So these were the 4 values in the first state, the next one, and this is a batch of 32. So as you can see, we're going to have 32 states in this. But there you go. So this is how we split it up. Now, next step that we need to do is get it ready to be passed into the neural network, because remember, we're training this in the neural networks. And if you remember, one of the important things is that to pass it through a neural network, it needs to be as a tensor. So we're going to take each of these and we're going to make it a tensor. So torch.asTensor. I'm going to copy this and paste it so we can do it for each and every one. And I have to update this as well. Okay, awesome. So now we have the different batches of each of the different things, but now they're in the form of a tensor. So now the next thing we're going to do is we're actually going to pass it through the neural networks, make the original guess for the online network, and then we're going to make the better guess for the target network, and then we're going to compare the two. Okay, so I just realized there's actually one more thing we need to do, which is, if you can see here, right now, the states is in the right form, right? We have the batch dimension, there's 32 different states. But if we, for example, printed, sorry, I have to recopy and paste this. So I'm gonna do that real quick. So basically, if we print actions t right now, and we run it, as you can see, we have the list of all the different actions for the 32 times, 1, 1, 1, 1, but there's no batch dimension. It's all just in one long thing, which is not going to work when we try to do operations where we add or multiply or interact when we do actions and the states together. So we need to add the batch dimension to this. So what we would do here is we take this and we do dot unsqueeze -1. And what this does is if we rerun it, and we see that the action, we have each action for each state. So now this one would correlate to the first state, and they're both in the same form. So this dot unsqueeze, we needed to do that to the actions, but not to the states, because the states was already in that form. But we need to do it to the rewards, and we need to do it to the dones, because they are not states. So they don't have the courtesy of already having that extra dimension on them. So now that we've done this, all of the values will have the batch dimension added to them. So that's an important thing. So I'm going to add this to up here in our actual code where it is important. All right, so let's, as a first step, calculate or make the first guess of what the Q values would be with the online net. So we're just going to say Q values equals online net, and we're going to pass through it states T. So now that we've passed states T through it, the next thing to do is to choose the right Q value. And what I mean by this is, this has two values. It's the Q value for the first action, the second action, right? Going left or going right. But in the actual experience that we had up here, we only took one of the actions. So only one of the Q values actually matters, right? Because in this state, it doesn't matter what the Q value was for going left if in the end we went right. So we want to just find the Q value for which action we took, because that's the one that we're going to be comparing to what actually happened, right? We guess for what the Q value of that action should be. Then depending on what the reward in the next state was, we determine if the Q value for that action was actually the right Q value. So we need to choose the right Q value. So we're going to say action Q values, and we're going to choose the Q value based upon which action we took. So we are going to make the index actions underscore T for each state, or for the Q value, the two Q values of each state. It's only going to choose the one which has which is the same as the action it actually took. So we input the Q values, and then now we want to calculate the target Q values. So first what we're going to do is we're going to use the target value, the target network, because we use a different network, to calculate the Q value for the S1, the next state. And the reason for that is we want to get the values necessary to better calculating the Q value of an action. And in this case, the Q value that we originally calculated just here, the original guess, a better version of it would be to take the reward we get and add it with the highest Q value from the next state. So that's what we're going to be doing here. So we're going to figure out what all the Q values were from the next state. So we're going to pass new states T to the target network. And now here we don't want to choose one based on what the action was, but rather what the largest Q value is. So we're going to say target Q values equals target Q output dot max, not argmax, because we don't want to know which one it was. We want to know what the value of the highest one was. Mention true. And finally, if you remember, we do the 0 for the same reason that we did it up there somewhere, which is that we're indexing in and grabbing the specific value within the tensor. So now that we have it, we want to find what the optimal Q value was. And this is where we write the Bellman equation, quote unquote, plus a few things, because we want to have the learning rate as well, into code. So here we go. Optimal Q values equals rewards T plus gamma. And now we add this little part here called 1 minus duns T. And I'll explain what that does in a second. Times target Q values. And if you disregarded this right here, this part right here, this would be the equation for calculating what our best guess of the Q value would actually be. So now we have, for this state in action we took, we have an original guess that we passed through the online network, and then we have a better guess, which is passed through the target network, and this one took into account both the reward that we got from taking the action and also what was the highest Q value at the next state. So this one is a much better guess. Now we add this 1 minus duns T here because if the game ended at that point in time, if let's say the agent failed, done would equal 1, right? Because the game would be over. And at this point, 1 minus 1 would be 0. and it would take the Q value and it would make it equal 0. And why is that what we want to happen? Well, because when the game ends, there's no more value to get, right? The game is over. There's no reward in the future that you could get from staying alive. You're already dead. So at this point, it would say, okay, the optimal Q value when the game is over would be 0. So that makes sure that at all the final states, the Q value is 0. So now that we've calculated the optimal Q value and we've calculated the initial guess Q value, we need to compare them to one another to train the online network. So we're going to calculate the loss between the two. So we're going to do the smooth L1 loss, and we want to find the difference between the original Q values that we calculated, the action Q values, and the optimal Q values, which is the better guess. Oh, whoopsies. All right, optimal Q values. So now that we've calculated the loss, we can then train the network. But we need to zero out our gradients, otherwise they'll just keep on building up over time, right? So we need to make sure that we zero them out. Then finally, we are going to calculate the loss for each one of the weights. So how much should we change the value of the weights of each layer in the network to create a better guess? And then we are going to implement it, optimizer. And here you go. These 3 steps has taken the difference between the optimal Q value and the action Q value, and it has changed the online net's neural network, its weights, so that way it can make a better guess in the future that's closer to the optimal Q value. So we have just trained the network. So now that's basically the bulk of what we need to do being done. One of the last things, if you remember when we were looking at the Google Doc and the steps, we need to update the target network so its weights are the same as the online network, right? Because we need to make sure both networks benefit from the training. So we're going to say if EPS count, remember EPS count is just the counter we kept of how far along we are, modulus 1000 is equivalent to 0. And this just means if EPS count is divisible by 1000, then do the following. So basically it's just saying every 1000 steps we are going to update the target net's weights. All right, there we go. So now every 1000 episodes, it will update it. Finally, just so we can understand what's going to be happening, so we can see as the coder how well it's doing, every single time an episode is done, we're just going to print how long it lasted. So we're going to say print step. And also we need to break from the for loop so we can start over it can break from this for loop and it can start over another episode. So we're going to say break. This would get us hopefully into a trained agent. The last thing I'm going to do is add a little thing that once we've solved it, it will render the environment so we can see our AI play, so we can see it play the game like efficiently, so we can feel the satisfaction of our work. So I'm going to code that in really quickly. Okay, so the game is considered beaten if the agent can keep the stick up for 195 steps. So we're going to say if step is greater than or equal to 195, we have completed the game. And remember, step was the variable we calculated in this, so it's just going to be the amount of time steps in the episode. So we're just going to create an infinite loop, so that way we can just see the game play over and over again, and whenever you get tired of it, you can just stop the code from running. But that way it'll just keep on playing. So while true, infinite loop. And what we're going to do is we're just going to constantly exploit the environment, and we're going to trust that our agent has learned enough that it will be able to beat the game. So we want to pass it through onlinenet.act, take the state, and then at this point, the only thing we need is state and done, because we don't need to do any training with the reward. So we just need state can do an underscore, which just means nothing. We won't get anything from it. So that way, all the information we receive is state and done. And then we equals environment.step action, because we need to have the state to calculate what to do next. And we also need to know when the game is done so we can restart the next episode. .render, and then we're going to say if done, state equals environment.reset, right? We reset the environment. Awesome. Okay. So now that we've done this, we can run the training loop and make sure our code is all doing great. But the first thing that I would suggest you do too is just run through all the blocks of code, because you need to make sure all these blocks of code are running and working before we get to the big training loop. All right, and let's run it. Open. Looks like we've got I misspelled epsilon decay rate. So let me go up here. Silly me. All right, there we go. And run it. And you'll actually find that you get quite a decent amount of errors. It just, since we coded all this, we're gonna need to kind of go through, clean everything up, and make sure that we did it right. So let's see what we got. And I'm just realizing for actions.t, I did torch.float32, but the action is just 1 or 0. So we don't need it to be float32. In fact, we want it to be int64 because it's just an integer. So let's run this again. As you can see, this is how long the states last, and over time it will hopefully get better and better. So let's wait and see what happens. Okay, so I realized that you actually couldn't see my whole screen. You could only see my tab, so you didn't understand what exactly was going on. But basically, in the beginning, its actions weren't great. Over time, it kind of slowly got better and better and better. The steps got longer and longer and longer until it got into the hundreds. And then finally, it stopped here. And the reason it stopped here is because one episode hit over 265, so it entered the infinite loop. So now if we click on this, we'll be able to see that now it's just an infinite loop, and it has the environment rendered where it's able to balance the stick. So you can just watch this for a little bit. It's satisfying to see the agent balance the stick. And you can see it's much better than on the gym website, when we could see it was just falling immediately because the agent was just moving randomly. But yeah, there we have it. Like, this is pretty sick. I know it's not AI that's taking over the world or anything like that, but it's an intelligent, to an extent, an intelligent agent which has learned this environment and learned how to play the game effectively. And that's pretty badass, if you ask me. So there you go. There's the first implementation of deep Q learning. Pretty cool stuff, but this is just the beginning of the reinforcement learning journey. So I'm going to be tackling now robotics and reinforcement learning. How can we use reinforcement learning to create an agent which learns how to act in real life? This is going to be a lot more complex, but I plan to either continue on this YouTube channel or create a new YouTube channel. I'll link to that. I'll let you guys know, where we do this, but on a much more complex and complicated scale, where we can create robots which actually automate tasks. And that's going to be pretty cool. So I'll keep you guys updated on that. If you want to know more, you can check out my LinkedIn, my Twitter, in the description. I'll have my socials down there. And I'm excited for you to be with me on this journey where we can learn to create artificial intelligence that really makes an impact in our world, because this is just the beginning.